Okay, welcome back to the last session. Kicking things off, we have Schramm, who's a assistant professor at Stanford, and before that was in Cambridge, and before that was here. Talk about computational variance estimation from low-degree polynomials. Take it away.
Thanks, Sam. All right, I think this is my first in-person talk since before the pandemic, so I'm like a little bit nervous actually standing up here, but it's a sea of friendly faces covered by masks, so we should be good. Okay. All right, so the title of this talk is Computational Barriers to Estimation from Low-Degree Polynomials, and this is based on joint work with the wonderful Alex Wine. And the setting of this talk is trying to understand the computational complexity of planted problems. So setting, we basically we're given input, which consists of a signal perturbed by noise. So to make this more concrete, let's focus on a specific family of models, spiked Gaussian matrix models. So here I have a distribution P lambda, and a sample from P lambda has the following form. It's a n by n matrix X, which is given by a rank 1 spike plus IID noise. So the law is that every entry of Z is independent Gaussian, and every entry of V is sampled independently from some prior mu. Okay, so depending on this prior, you can kind of capture different scenarios that you want. For example, if mu is some sparse prior, like Bernoulli K over N, then this is some kind of version of sparse principal components analysis. And the idea is that you have a bunch of a matrix of data, and you want to understand how things are correlated, and there's some sparse subset of coordinates that are positively correlated. Okay, so here this is called the planted submatrix problem. But by changing this prior, you can capture all kinds of different scenarios. And okay, the idea is that this is a simple yet pretty faithful model of problems that we encounter in statistics, like principal components analysis problems. Okay, so there are two natural algorithmic goals that we might associate with a planted problem like this. So algorithmic goals. So the first is estimation or recovery. Okay, so here given X sampled from P lambda, the goal is to find V. Okay. The second goal, which is, so this is kind of like a search problem. There's also a natural kind of decision variant of this problem, or testing. So testing or detection. So here we're given X, which is sampled either from P lambda or P0, and the goal is to decide which one. So actually this at this point I realized that I forgot to say something that's kind of important, right? So here we have this lambda sitting in front of this rank 1 spike. So this is like the signal to noise ratio, which I'll abbreviate SNR. And as lambda gets larger and larger, the problem should become easier and easier to solve because you have more and more weight on the planted vector that you want to recover. Okay, and here, if X is sampled from P0, right, that's like no signal noise ratio, meaning it's just pure noise. Okay, so in the detection or testing problem, we want to decide if there's any planted vector at all, right? So this is like the decision version of this search problem. All right, so the title of this workshop is Rigorous Evidence for Information Computation Gaps. So it shouldn't surprise you that for this problem, there are information computation gaps. So. Okay, so I spent a really long time as I was preparing this talk, trying to figure out what the phase diagram should look like. So I very proudly present to you what I've confirmed with Guy Bressler is a correct phase diagram. Okay, so let's say that I'm in this planted submatrix problem, and I'm going to parameterize it as follows. I'm going to let K be like n to the alpha, meaning the vector has n to the alpha non-zero entries on average. And I'm going to set lambda equal to n to the beta minus alpha. Okay, and here I'll let alpha range from 0 to 1, and I'll let beta also range from 0 to 1.
This makes it a unit vector or something? Is this the...
Yeah, beta is how much I'm promoting it above being a unit vector.
Okay.
So the minus alpha is like, yeah, exactly. Okay, so this is what the phase diagram looks like. So in this region, both goals, estimation and testing, are easy. In this region, both are information theoretically impossible. And in these three triangles, things get pretty spicy. So okay, so in this region, both are conjectured hard. And in this region, testing is easy, but recovery is impossible. And in this region, testing is easy, but recovery is conjectured hard. Okay, so we have a pretty interesting landscape here. Oh yeah, apologies in advance for not, so I thought about how to cite this in a board talk. Like, there are at least 15 papers that are responsible for each of these various lines. So in lieu of citing these, which we do cite it in the paper, but live, instead, if you've worked on this phase diagram, please raise your hand. Come on, Guy. All right, good. Yeah. All right. Props to, yeah, I think I saw you jamming earlier, but anyway, okay, if you've worked on this, I applaud you greatly. Thank you for your service, and you are cited in our paper, which is on archive.
Yehan's probably on Zoom watching too, so Yehan's raising his hand in his office.
Good, good. Okay, cool. So this is what we have, and what we want to do is we want to offer evidence. Okay, so you can see that, you know, in the regimes where things are beta going, raising your hand next. Okay, so in the easy regime, we have proof that it's easy because, were you going to say something, Guy? Oh, sorry. Okay. All right. So in the easy regime, we know things are easy because we have efficient algorithms, right? And in the information theoretically impossible regimes, we know information theoretic impossibility because, you know, you prove some bound on the total variation distance between the two distributions or something like that. But for the hard regimes, we don't really have the same kind of concrete evidence, but we do have some evidence, right? So the whole goal of this workshop is to provide evidence for computational complexity. Okay, and so let me lay out a little bit of the evidence for hardness that we have. Okay, so so first for the testing problem. Meaning that this little triangle here is hard. So for this, we have a variety of different lower bounds against restricted models of computation, but we also have reduction, so evidence based on reduction. So we know that based on reduction from planted clique, that this regime should be hard for testing. Okay, and then here I was going to cite Ma, Wu, 15, and Brennan, Ressler, and Huheil from 18. Okay, so I think this is pretty good evidence for computational attractive-lit. If you believe that planet clique is hard, then you also believe that.
So,
Yeah.
what does planet clique being hard mean? Like, what's the threshold you're using here?
I believe that for every region in this point, you have a different planted clique hard point that maps to it. So, but I think if you believe that square root n is the upper bound, then this whole region is substantiated. Okay, guy. All right, cool. Okay, but now for recovery, our evidence for hardness has so far not been as strong. So for recovery / estimation, so for recovery and estimation, there are reductions, but the reductions are like, I think each of them leaves something to be desired, right? So there are also reductions from planted clique. So, oh, sorry, it's not from planted clique, from densus K subgraph or planted K subgraph. So this is also in this work. But here you have to assume that there's a detection and recovery gap in the problem that you start with in order to get a detection and recovery gap here. And there we don't have a strong evidence for detection and recovery gap either. So that's one thing. There's another reduction that's due to Kai, Liang, and Rocklin from 17. But here they end up with a slightly more complicated noise distribution in the output. So it's not strictly speaking for Gaussian noise. Okay, and then there are a couple of algorithm or lower bounds against restricted models of computation. So lower bounds against MCMC and also AMP. But the problem with these lower bounds is that MCMC and AMP are known to sometimes be beat by other algorithms, like, for example, for tensor problems. So if you have that these models don't work, that's not necessarily the strongest evidence that no algorithm can work. Did I see you raising your hand?
Yeah. So for this densus K subgraph thing, this problem is just like the Gaussian version.
Yeah.
Right. So this is just kind of some reason to believe that you shouldn't care about the noise distribution or something.
Well, I guess, like, you can maybe think of it as a universal. I mean, Guy probably knows better, but maybe you can think of it as a universality like result for the noise distribution. But you do need, you do need to assume that is harder.
Yeah, it's not the same as DKS, right? Like here, within it's more like clique, right? Because all the edges exist as opposed to
Yeah.
deleting some.
The Gaussian noise inside the clique is kind of like okay, I don't know. I mean, it's debatable. Okay, so that's what we had so far, and then our main result is a lower bound against low degree polynomials. So let me just circle this in a pretty color. So this is kind of our main result. We get lower bounds against low degree polynomials that show that the testing or that the recovery problem is hard even in this regime where the testing problem is easy. Okay. In fact, we get so what we're doing is we're substantiating this detection recovery gap over here. And one thing about the low degree polynomial model is that it does seem to be consistent, as far as we know, with the thresholds for efficient computation for other algorithms. So even though this is only a lower bound against a restricted model of computation, we do get an unconditional lower bound against a model of computation that seems to capture, it seems to be tied with the best algorithms that we know so far. Okay, so that's kind of the high level picture. And now in order to tell you more precise results, I need to give you more background, but I think I only have, do I really only have 5 minutes left?
No, that clock is fast. You have 9.
9 minutes left. Okay, great. Okay, so here's a little bit of background. Maybe I'll erase all this stuff. Okay, so here's some background. Okay, so the following is a quantity which is supposed to measure how well polynomials of degree d can hypothesis test between the planted and null distributions, between p lambda and p0. So LD, I'm going to define this to be the max over all polynomials in the input of degree at most d, where I take the expectation under the planted distribution minus the expectation under the null distribution divided by square root the variance under null. All right, so notice that if this value is of order 1, then there's no polynomial whose value can give a hypothesis test which succeeds with high probability, like with a guarantee given by Chebyshev's inequality or something, right? Because the variance overwhelms the difference in the means. So if LD is at most order 1, no degree the polynomial can hypothesis test. And another cool thing about this quantity is that actually it has a nice closed form, right? So the closed form for this is I just take the likelihood ratio of the two distributions. I subtract 1, I project the span of polynomials of degree at most d. Okay, and I take this norm in the P0 basis. So if you don't know what this means, don't worry about it. If you know what this means, you can like it. This is kind of like taking the chi-squared distance and projecting two functions of degree d.
So still just one quick question.
Yeah.
When you mean no degree d polynomial can hypothesis test, do you really mean like thresholds of degree d polynomial, right?
I mean, if you want to take the value of it, actually, I don't mean thresholds of polynomials. What I mean is if you want to take the value of a polynomial, so here this is saying that the difference in the expectations is overwhelmed by the variance,
Yes.
by the standard deviation under the null distribution.
Yes.
So this is precisely what I mean.
I mean, I think intuitively it should
Yeah.
mean that no threshold just of a low degree polynomial
So
distinguishes.
that I think is probably formally possible, but like in
But this
principle, you could-
doesn't establish it, right? Like,
yeah, like that's what I'm saying. Like, you could, I don't know, for all you know, you could look at the parity of the polynomial, and that somehow could tell you something more, even though.
I think even with thresholds, you can sort of play this trick, right? Like you can make like weird delta functions showing up or something. I mean, I'm not sure, but it needs some work to formalize it. But I guess, I mean, they can't hypothesis test in the sense that if you look at its value and you ask that it falls above some range, probably this won't work.
Okay, so then threshold. That's threshold.
Yeah, well, I get, but okay, yeah. I don't literally want to claim anything about thresholds. I just mean that this type of guarantee won't work. Yeah. Okay, so here is a conjecture, which let's attribute it to Sam Hopkins in 2018. So the conjecture is that for any nice planted problem, degree. So okay, if L polylog n is order 1, no polynomial time algorithm it tests. Okay, so this conjecture, it might seem very strong, right? It's sort of saying that this quantity has the power to capture all polynomial time algorithms as long as you take the degree to be logarithmic in the size of the input. But so far, this conjecture stands at least if you allow, some class of nice. But for example, the nice class contains all additive Gaussian models and many more. Like this so far yields consistent conjecture for planted submatrix, for tensor principal components analysis, sparse principal components analysis, planar clique, stochastic block models, many others. Great. But okay, if you look at this is really tailored to say something about hypothesis testing, right? I mean, we're really asking about the difference between P lambda and P0. So what should you do for estimation? So that's really what the subject of our paper is. And then for estimation, we study the following quantity, which I think is fairly natural. So it's the MMSE D, the minimum mean squared error of degree D. So this, I'll define it as the minimum over all polynomials, degree at most D in the input of the expectation under the planted distribution of the squared difference between the polynomial and, let's say, the first entry of V, right? So by symmetry, the first entry of V will capture everything squared. Okay, so this is the degree D minimum mean squared error. It's asking how well can a function of degree at most D estimate the first coordinate of our planted vector. And this is a very natural quantity, but it's very unclear how to bound it. There is no similar closed form. I thought I had more time. I thought I wouldn't take as much time to get here. Sam's telling me I have 2 minutes, so let me just cut to the chase immediately. So, okay, so the theorem. Can you see if I write down here? Okay, so theorem. So in this red region, the degree polylog n MMSE or planted submatrix is like k over n minus k over n squared minus little o1, which is exactly what just using the function f of x is equal to the expectation of v1 would give you up to this little o1 factor. So in other words, we're showing that no polynomial of degree at most polylog n can achieve non-trivial estimation in this whole red region.
How small is the middle form? Or like when does it form?
Yeah, it's very small. Like even if you allow degree n to the epsilon, still this is a little o1. But I didn't want to I mean, yeah, I don't want to write the whole parameter trade-off because just like
Little of one means k, little of k over n squared or something.
Yeah.
Okay. It's smaller than all the other terms.
Yeah. Okay, great. Let me also just say that I stated the theorem for planted submatrix, but actually we get a characterization or some kind of upper bound on the MMSE at degree D for any additive Gaussian model and any binary observation model. And we have an analogous theorem for the planted dense subgraph problem or the dense K subgraph problem, substantiating the difficulty of recovery in the region where there's a detection recovery gap.
Sorry, so what is this lambda show?
Yeah, so lambda, I was kind of hiding. I mean, it's here, right? But I'm just, so this whole map encodes that. So like, lambda is fixed by beta and alpha. So for any lambda falling in this kind of slice. Yeah. Yeah, great. So that's the result. I guess I had planned to tell you a little bit about the proof, but I guess I don't have time, but I'm happy to talk about it later. Let me just say that I think the open directions are ample, because even though we were able to say something non-trivial for any additive Gaussian or planted, or sorry, binary channel model, there are many other models that aren't covered by this result, where we still don't really know how to substantiate computational intractability when there's a detection recovery gap. So my favorite problem is over complete tensor decomposition. If you have ideas, please come talk to me. Yeah, and thanks so much for your attention.
While we change over to Zoom. Yeah, Guy.
Yeah, so first off, I recommend everyone look at this paper because it's beautifully written. I reread it last night. I have a specific question here about your prior, and there's something interesting with the prior. So if you have something that's symmetric, like +1, -1, then there's no detection of every gap.
Right.
So imagine you can get from your results some understanding of like what exactly sort of the amount of asymmetry in the prior
Yeah,
leads to it.
I think that if you wanted to encode it, if you wanted to do a different prior, but you want an additive Gaussian situation, we have some upper bound on the degree D minimum mean squared error. And it's just a matter of calculate. I mean, it's some calculation. Like it's a calculation that's maybe not that dissimilar from the like usual low degree likelihood ratio calculation
One
that
can
you have to
maybe
do.
characterize like when
Yeah.
they diverge and when they.
Yeah, totally. Yeah, that's totally on the table. Yeah.
What's the detection algorithm? Is it an easy immediate algorithm?
Yeah, you just take the sum of the entries of the matrix.
Okay.
In the regime where there's a gap.
Yeah.
Yeah, so easy. Yeah.
So since the typical detection threshold proof doesn't work, how can you give an idea of like what you change for recovery?
Yeah, so it turns out that this quantity is actually fairly different than the other, because you're not sort of comparing, instead of constraining the variance of f under null to be small, you're constraining the variance of f under this planted prior to be small. And that's a much stricter restriction. And that's sort of what makes the value smaller. And it's more challenging to carry out the calculations because of this, but we were able to overcome this in a way that's like still fairly magical to me. And I don't really have intuition for why it worked. Yeah. Oh, sorry, Tim. Yeah.
Is this the same minimization from Hopkins and Stoyer where they do
No.
the stochastic block model thing, or?
No. So in the minimization in Hopkins and Stoyer, exactly the thing is that the variance is bounded under null instead of under planted. And for block models, that's a small enough distinction that it doesn't make a difference. But here, where there's a detection recovery gap, there is a difference.
Okay. And were you to use that, things would turn out differently.
Right. Yeah, you wouldn't get anything.
Okay.
Yeah.
I mean, maybe it's a small enough difference in block model that it doesn't make a difference in the thresholds you get, but it's still the case that the one that we did doesn't make any sense. like it's just cooked up so that we can prove something. Okay, other questions for Tselil? Okay, thanks, Tselil.